This video is partially part 6 of the milling machine restoration series, but I'm also going to cover a lot of information regarding VFDs, and there's going to be a low RPM, low hertz torque test, as well as some electrical and configuration information. I put that warning there because if the pulley is stuck, you most definitely can crack it very easily, but in this case the PB helped it come right off. So the motors look surprisingly good inside. They were sealed up very well. And just like every electric motor I've ever worked on, the rear bearing is always the one that's bad. Why they don't make both of them big, I have no idea. If somebody out there knows, please tell me. The only thing I can think is it's just engineered obsolescence, because putting the small bearing in there just makes it wear out faster. So both of these motors, the front bearing was good and the back bearings were toast. I found a great deal on eBay for some motor specific bearings, which can be quite pricey, but you can see by the date codes on the packages they're pretty old, but they were still sealed up and wrapped in the corrosive paper, so they were like brand new, and the grease wasn't dried out or anything. They were very smooth. I was very surprised, and I got a great deal, and they actually predate the milling machine, which I believe was manufactured around 1974-ish. This is the motor tag off of the horizontal motor, and you can see that it's 1.5 horsepower and 5 amps, and the vertical motor is 3/4 horsepower and 3 amps at 230 volts. That's the only real difference between these two motors, is the horsepower and the amperage, and that becomes important later. So I'm sure that a lot of you are very familiar with this tag, but a lot of people are not, so I'm going to cover it anyways. So if you look at the top of it, it says 3-phase motor, connect line leads to 1, 2, 3. So those are your 3 incoming phases. We're dealing with a 9-lead motor, and again it's 230 volts. So there's also 1, 2, 3 inside of the junction box on the motor. Those connect to 7, 8, 9, and 4, 5, and 6 are ganged together. So it's pretty straightforward, and this is pretty universal for most 3-phase motors, but yours may be different, so look at your tag. You also need to know what's considered the forward direction of rotation on your motor. For example, on the vertical motor, it needs to go counterclockwise in the forward direction. That meant that I actually had to reverse 2 of the leads in order to reverse the direction of rotation, whereas the horizontal motor was just straight up 1, 2, 3, and I didn't have to reverse anything, and it was going clockwise in the forward direction. Alright, so now let's talk about parameters, or PIDs, process IDs. This information applies specifically to TECO VFD L510 models. The VFD comes default set to VF mode, and what you really want is SLV, which is sensorless vector control. Without being long-winded or complicated about this, basically SLV is trying to keep the torque level up even though the voltage level is dropping. So if you drop below 60 Hertz, it's trying to keep that torque level up higher, whereas in VF mode that doesn't happen. In order for SLV to work, there's a few PIDs that we need to address first, like the amperage, the RPM, and the horsepower or kilowatts, and the motor rated hertz. So you can get all of this off of your motor tag. You do have to do a conversion for horsepower to kilowatts. It's easy to find online. And in my instance, I'm not going to use 07, which is auto tuning the motor. If you're just using one motor, then you should do that. But if you're using multiple motors that are dissimilar, then you should not do that. And here's a few more general purpose PIDs that you may want to know about. By default, the potentiometer on the pad is set as the primary frequency source. I have an external potentiometer, so I had to change that. The upper frequency limit is just the amount of hertz that you want it to go to, what's your upper threshold. So I've got mine set to 100. Usually they say it should be around 90. I set mine to 100 just to make it more in line with the scale that I have. The acceleration time I have set to 3 seconds. Kind of think of that as like soft start. And deceleration time also at 3 seconds. So it does DC injection braking to slow the motor down. And I figure 3 seconds is a good trade-off. I'm not putting too much stress on the VFD or the motor. And again, without being overly complicated, the carrier frequency is just simply how fast the switching is occurring inside the VFD. And I'll cover that more in the next clip. Carrier frequency mode is whether or not you want two-phase pulse width modulation or three-phase. It's set to two-phase by default, so I went and changed mine to three-phase. And extended display mode, which allows you to change what you see on your display whenever you push the mode button, like temperature for instance, which is not set by default. Alright, so hopefully all of that did not cause your head to hurt, and we're going to circle back around to the much talked about carrier frequency. Basically, how fast is the pulse width modulation occurring in the IGBT, which is in the VFD? By default, the carrier frequency is set to 5 kilohertz, which means that it's audible when the motor's running, and has a range up to 16 kilohertz. Now you'll see in the next clip that I set mine to 16 kilohertz, and I'm sure you've heard about it or read about it, that you can burn up the windings or melt the wiring or burn up the bearings. A lot of bad things can happen whenever you set the carrier frequency very high, and that you should be using an inverter duty motor. The VFD that I have is rated for 2 horsepower, which is overrated for the motors that I have, which should be ideal to be able to run the motors at 60 hertz, which is what I intend to do most of the time, and underdrive on occasion, but not really overdrive it. I can overdrive it if I want to, but so far in the testing that I've done, I haven't experienced any overheat condition. I've never seen the motor get above 98 degrees, and I've never seen the VFD go above 94 degrees Fahrenheit. Alright, so with all that said, this is what I'm doing. Adjust your PIDs at your own risk. I don't want to talk during the next clip so you can hear what's going on with the motor as I change the carrier frequency. And you may hear some bearing noise, but that's because I actually did this test before I got my new bearings. So I have an old bearing that I used as a replacement for the bearing that was in the motor that was no good. There's the VFD junction box mocked up. I decided to put it on the left to leave room on the right for a DRO. The slots on this table are kind of small and oddly sized, so I had to make some small pieces out of flat bar so I can get my small vise mounted to be able to make some proper T-nuts to get the closing vise here mounted. And I've had this broken wrench in my toolbox for years. I welded it back together and put it back to use. And there you can see I've got some hardware sorted out finally, and I can get the big vise mounted on the mill. I made a heatsink to go on the back side of the VFD junction box. I can't mount the box straight to the casting because of the taper of the casting. It has to be on a standoff. So I figured, hey, I'll mount a heatsink on the back side of the box to help dissipate heat. I don't know that it's strictly necessary, but it didn't cost me that much. I already had the aluminum, and the heat sinks I picked up on eBay for next to nothing. Just took a little work to get it mounted. Alright, there it is finally. There's no less than 25 holes in that box. The switch on the left is the master power, and the switch on the right is the motor changeover switch. To the left is the horizontal motor, and to the right is the vertical motor. In the center is off. I've worked with several different models of VFDs, different manufacturers, and this thing is great. Whenever you flip the switch and you see the hertz flash, it's ready. You can flip it on immediately. That's the RPM sensor for the vertical spindle. I mounted the magnet in the bottom of the pulley in one of the counterbalance holes. Maybe not the best solution, but it was the best place I found to put the sensor. Here I'm just validating what's on the spindle speed tag. And you can hear that once the motor gets up into the 4400 and 6300 RPM range, it doesn't sound happy. I have the belt on the 300 RPM pulley and the VFD set to 100 Hertz. I just want to see how much over I can go in that range, and basically I have overlap in all ranges. So I don't know what the official name of this test is, the grab test. Anyways, I have it set on the 300 RPM pulley, and the VFD is on 25 Hertz, and I cannot stop it, or even slow it down much for that matter. Alright, so this is the beginning of the torque test, and I've got it again on the 300 RPM pulley, and I've got it on 25 Hertz, so it's 150 RPM is really what my target was. And this is not super sharp, but not dull half-inch drill bit with no pilot hole. And I'm applying a lot of pressure to it. Alright, so this is not a brand new bit, but it's only been used a few times, and it is an import bit. It's not that good a quality. You can see that it gets a little wobbly here and there, but it seems to be doing the job, and I'm really laying on it hard. I'm not backing off at all, and you can see that I'm bogging it down a little bit, but not much, and it's going through it. If you'd like more information or you have questions, please comment below. I could talk about this stuff all day. Well, what am I saying? I have been talking about stuff like this all day. Thanks for watching.